Compilation.
Hi there guys, I'm Chris Bowden with the Geek Group, but you can call me Batman. Today we're going to take a moment and talk about resonance, because this is a concept that seems to elude a lot of people. So we're just going to take a minute and talk about the very simple concepts of resonance. Resonance works kind of like this. This is our heavy bag of science. Inside the heavy bag is actually a gentleman by the name of Herr Zapp. If we take the heavy bag and apply energy to it through the use of this 34-inch lever, and we apply, let's say, a large impulse of energy by something like that. Now that's a couple hundred watts there. That's a lot of power. Now you'll notice the bag moves, but not a whole lot. Now if I just start applying energy at random times by doing something like, the bag doesn't move all that much. And that's because I'm just applying random bits of energy. Now it's all about the same amount of power, but the timing's off. Now resonance is important with timing. So what you do is apply a small amount of energy with just one hand, but if you do it at the right time. Now there's a lot less energy here. I'm just doing this with my fingertips. But by doing it at the right time, I get a much bigger result because I'm doing it at the resonant frequency of the system. Because the bag and the rope, the whole pendulum setup there, wants to move at a certain speed, and it's like a kid on a swing set. It's very, very simple. And all you have to do is put in a little bit of energy at the right time, and you get a big result. Now the amount of energy isn't nearly as important as the frequency that you put the energy into it. It's also important to have a really good mount up in the ceiling, which we don't right now. But watch, we'll show this again with the same timing, but a higher amount of energy. Now if you take and you wait, now you'll notice even though it's swinging farther, I still have to hit it at just about the same time, even though it travels further. The hard part is trying not to hit other things too. It's so going to fall down from there. So that is a basic example of how resonance works. Everything has its own resonant frequency. And this is true of mechanical objects, physical things. Even this bat has a resonant frequency. You can hear it. If you smack the bat on the ground, it rings. That's a couple kilohertz. It's a pretty high frequency, but it makes a sound. That's the resonant frequency of this wooden bat. If it were aluminum, it'd probably ring at a higher frequency. Electrical circuits can resonate too, and that's how a Tesla coil works. So let's look at the schematic of a Tesla coil. Now we start with our primary. Now here is our Tesla coil circuit. Now we have the low voltage side over here, and this is, say, 120 volts. Now this would be your neon sign transformer, this happy little box here. So you would have, say, 120 volts on your primary here, secondary of 12 or 15,000 volts. And what this does is you're putting energy in here all the time. This energy is being used to charge your capacitor right here. So the first circuit is there's actually, it's like two separate circuits here. You've got the charged circuit and the discharged circuit. Now we'll do the charged circuit in red so you can get the idea. The charged circuit is where this transformer secondary is working like this, and it's slowly putting a charge into the capacitor here. So that builds up the energy. That's swinging back with the baseball bat, getting the energy built up. Now once the capacitor reaches its full charge, because until the capacitor is charged, it's a load. So once that's charged up, the voltage raises, and the second circuit comes into play. And that's where we have here, because this throws a spark across the spark gap, and that dumps this huge impulse of energy out of the capacitor and through the primary coil, and this is the big primary coil out at the base of your secondary. And that puts a big shock wave, a big impulse through there. So that's the hitting it with the bat. And then here, out on the high voltage side of the world, that impulse gets pumped into the secondary coil electromagnetically. It's done through electromagnetic inductance. And when that impulse is pushed into there, it pumps into this system. And this is the electrical equivalent to our heavy bag. You pump a bang of energy into it at the right time, and it builds up, and it builds up, and it builds up, and pretty soon the bag is swinging from one end of the room to the other. And that's the basics of how it works. It's using electricity to create a resonant circuit. And by changing the value of the capacitor, you can change the resonance of this circuit. If you want the bangs to be bigger, if you want the voltage to be higher, you increase the voltage on the power supply and open up the spacing on the gap. Because this is a voltage-controlled switch. And a spark gap is pretty much the simplest form of switch there is. If you have two electrodes and they're that far apart, well, that might take, at that voltage, let's say, of 20 kilovolts. Okay? And these, at 19,000 volts, won't conduct electricity, because it's whatever the distance from here to here is, determines the breakdown voltage of the gap. And there's a lot of other little things that'll affect it, like the humidity in the room, and the air pressure, and whether or not you're doing this on Venus or whatnot. But, normal air, there's set formulas for it. So this might break down at 20,000 volts, but if you move the balls this far apart, it might take 50,000 volts. And, it goes up with the spacing. So once the gap is sitting at 19,000 volts while this is charging, it doesn't go bang. But once you've reached the breakdown voltage of the air between the balls, boom, a spark jumps across, and now the switch is closed, and that completes your circuit. So that's how this works. So if you change the gap spacing, you change the voltage that it fires at. If you give this more time to charge and make up more voltage, you get a bigger bang. So there's also variables in there with taking into account the size of the capacitor and all that stuff and its values. And there's a lot of math to it, but this is just a quick basic overview for all the people that are just getting into this that wanted to learn about the basics of resonance. And we play with a lot of other resonance too. We do a lot more than just electrical resonance around here. We play with the dancing goop demonstration that everybody knows and loves, works on mechanical resonance. So we're going to shoot a video sometime soon on the dancing goop, because I don't think we've ever made a video on that, but a lot of people have come and seen it in person. For those of you that have been to one of our shows here, that's the one with the big speaker and the dancing goop. So yeah, you get an idea. So yeah, there's your quick look at resonance. We want to thank everybody who made this video possible, especially Herr Zapp, because I don't know anything about Tesla coils. I'm just getting started in this. I'm really new to it. So I want to thank him for writing in and really teaching me the basics of Tesla coils so that I could go and learn all this stuff. I really appreciate your help on that. So thank you, Herr Zapp. I want to wish you all the best. You guys have fun. I'm Chris Bowden with the Geek Group, and next week I'll be off Broadway playing Batman. So you guys have fun. We'll see you next time. We're going to get back to work.